So there are two major types of descriptive statistics. Measures of central tendency are the first type. So measures of central tendency, the first question we should be asking is, what exactly does this mean? Central tendency is the way that data tends to cluster around some central value. Now, there are different ways that we could talk about centrality in statistics. There are three major types of measures of central tendency that discuss centrality in a different way. So there's the mode, the median, and the mean. The mode discusses centrality in the sense of what occurs most often or what's common. So the mode is defined as the most frequently occurring value in a set of data. Now, the mode is particularly well suited for nominal data. Nominal data is data that can only be characterized by frequency, because nominal data does not contain real numbers. When data is measured on a nominal scale, it means that the numbers are merely placeholders for words. For example, if I was to talk about sex and broke it down as a binary variable, that means it takes two values, male being one and female being the other. I could call male 1 and female 2. But these 1s and 2s aren't truly mathematical values. For example, I cannot say that if I add 1 plus 1 and get 2, that in fact that translates to the variable, because you cannot say that it takes 2 males to equal 1 female, although my wife might say that's true. Now, when you talk about distributions, the peak of any distribution is going to be the mode. So when you look at it as like one of those curves, the highest peak in the histograms you created last week would be the mode, because that means those numbers occur most often, hence the high peak. So any non-uniform distribution can be characterized by the mode. Now, a uniform distribution is a distribution that has no mode. It will look like a perfect rectangle in a histogram because every single value occurs equally often. When this occurs, the mode is not appropriate. Now, you can have multiple modes, bimodal or trimodal data, which occurs when you have more than one number that occurs very frequently. So if I had a set of data and number 2 and the number 5 both occurred 30 times, and 30 was the greatest frequency with which any number occurred, then both 2 and 5 would be my modes, and this would be a bimodal distribution. The second option is the median. The median is the number that occurs at the 50th percentile. That is, it's right in the middle of your data. So this splits the data into two equal halves. You can locate the median in a set of scores by taking the count of the scores, adding 1, and dividing by 2. Now, please keep in mind, this is the location of the median, not its value. So what that means is, this tells you which number, when your values are in order, will be your median value. It does not tell you what that number is. It tells you where it is. So the median is suited very well for ordinal data. Ordinal data is data that has order, but not equidistance. Equidistance means that the numbers are exactly the same space apart. So an example, if I talk about run times in seconds, 1 second is always 1 second. And so somebody who's 3 seconds behind one runner and 8 seconds in front of another runner, that the distance of seconds is identical. However, if I talk about run times with respect to places, I could say someone got first, someone got second, and someone got third. Now, those are in order, but equidistance does not necessarily characterize those, because the person who got first may have been 10 seconds ahead of the person who got second, but the person who got second was a minute or 60 seconds in front of the person who got third. So notice the distance here between 1, that is first place, and 2, and the distance between 2 and 3 are not the same distance. So this would be ordinal data. When you have ordinal data, the median works quite well because it tells you who's right in the middle. The median also works well for data that is measured on an interval ratio scale. We'll talk about more on the next slide. That is highly skewed. So that means there are a lot of values that kind of hang out on the extremes, on either high extremes or low extremes, instead of having a nice kind of even bell curve shape. We'll talk more about that next week. So the median is often considered kind of a compromise between the mode and the mean for skewed data, because the mean will be dragged most and the mode will be affected least by skewness. We'll talk about that on upcoming slides. So the final option, and probably the most common option in the kinds of statistics we'll learn in this class, is the mean. This is the arithmetic average of a set of data. It's defined as the sum of the scores divided by the count of the scores. You see here in my notation, I've used y sub I as the notation for score. Many books use x as a simple placeholder for unknown values. Don't get confused by that. It's the same idea. It's the placeholder for a score. Sigma, what looks like a weird shape E, is a Greek letter. It is the capital letter sigma. And sigma is a summation operator in statistics. That means that you add up all the scores that follow it. So when you see sigma y or sigma x, it means add up all of the scores. Then you would divide by the count of scores. Now, the count for a population is annotated with capital N, but for a sample, it's annotated with lowercase n. It's the exact same idea. We just try to be specific to determine whether we're talking about populations or samples by using an uppercase or lowercase letter respectively. So when you see these, you would add all the scores and divide by the count. So if I had the numbers 4, 5, 5, and 6, n would be 4 because I have 4 scores. Sigma y or sigma x would be 20 because 4 plus 5 plus 5 plus 6 is 20. So then sigma yi, 20, divided by 4n would be 5. So my mean would be 5 for that set of data. The mean is very well suited for interval ratio data. Interval ratio data is data where the numbers are real numbers. Things like your height or your weight or time in seconds or speed in miles per hour. These are things where the numbers are real numbers. They have equidistance. So if you gain 5 pounds or lose 5 pounds, it's the exact same change in weight, right? If you weigh 5 pounds more than someone else and someone else weighs 5 pounds more than you, you're the same distance from both of them. Equidistance. The numbers are always the same distance from each other. Because of this, when you have interval and ratio data, we can do mathematical operations. We're going to kind of group interval and ratio together because for introductory statistics level, that is very common to do, although technically these two types of data can be distinguished by the presence of a true zero. That is whether or not 0 is a meaningful number on a scale. So as an example of a non-true zero, temperature in Fahrenheit does not have a true 0. To say that it is 0 degrees Fahrenheit does not mean that there is no temperature outside. Whereas the idea of a true and meaningful 0 would say that if you get to 0 on a variable, it should be the absence of that variable. In the case of Fahrenheit, that is not so. There is still temperature, albeit what we call a 0 degree temperature. However, if we were to talk about your income, if you had $0 of income, that is a true and meaningful 0. If you have no money coming in, it really means the absence of income, the absence of money, not just some arbitrary mark on the scale, and therefore that would be true ratio data. Nonetheless, they're often treated similarly in statistics, at least in introductory statistics. In a perfectly normal distribution, which we'll talk more about next week, all three of these measures of central tendency will be equal, which kind of makes the issue of distinguishing between them a little less important. It's kind of some of the beauty of normally distributed data. But in skewed distributions, the mean is most highly affected by extreme scores. And so because of this, the mean is best suited for fairly normally distributed interval ratio data. Now, the reason the mean is so highly affected is because the mean is a fulcrum. It's trying to balance your data set. It's not trying to find the perfect middle. Because if you think about in this example with someone who is larger and someone who is smaller, if we put the fulcrum, that is the horse, if we put that right in the middle of the board, then it would not actually balance the data as you see here. If we want to balance the data, what we have to do is slide the fulcrum closer to the very large person. What that does is minimizes their effect, and it balances the data perfectly. So this is exactly what the mean does. It balances the data. So when you have very extreme scores, the mean is going to slide towards the big numbers, right, in order to keep that platform on perfect balance. And so it's important to keep this in mind. This is why very extreme values can affect the mean. Now, the mean is calculated exactly the same way for samples and populations. The denominator looks a little different, but like we said, that is just because of statistical notation trying to be clear whether we're dealing with a sample or population. So in all cases, all you're doing is adding up your scores and dividing by the number of observations. So to summarize, here is a little cheat sheet what each of these central tendencies is and the cases in which they are best suited.